Hello everyone. In this video, we are going to talk about extendable hashing. So as I mentioned in the previous video that extendable hashing is a kind of dynamic hashing technique where your hash function sort of changes according to the size of the file. As the number of records increase, then it will adapt it so that the load is distributed nicely. Okay, let's begin the discussion on extendable hashing. So let's assume that we have a nice hash function, and let's say that that particular hash function is giving out b bit hash values. Okay, we can just assume that b is equal to 32 for now, and we'll not go, as I said before, we'll not go into the details of the hash function. Your hash function can be anything. It may have all that uniformness property and randomness property and all that. Irrespective of that hash function, your dynamic hashing techniques work. So basically what happens is, uh, in this extendable hashing, whatever may be your hash values which are getting generated out of a hash function, what the algorithm does is that it does not take the entire hash value to perform the hashing. So initially when the number of records are less, maybe it will use only the first I bit from the left side, right? So let's say that if your hash values which are getting generated from the hash function, if they are 32-bit in size, then what extendable hashing does is that at any point in time it will look only a prefix of I bits from the left side, right? So that means if this I value, at the current stage, if it is I equal to 1, let's say, right? So we will have 2 to the power I buckets in the bucket address table, right? If I equal to 2, then we'll have 2 to the power 2 equal to, that means we have 4 bucket addresses. So as now hopefully you're getting the idea. So basically what we are going to do is that as the number of records increase in your file, uh, there is a systematic way in which the value of I is also increased, right? But if your number of records in the file, they are not so much, even though your hash function is generating 32-bit values, will probably use maybe the leftmost bit or maybe at max 2 bits and so on, right? So this way, the algorithm, what it does is that as your file shrinks or grows in size, it changes the value of I, and along with that it changes the total number of buckets that your hashing will have, right? Okay, so we'll go into more details, but let's see an snapshot of the whole data structure at any point in time, right? So in extendable hashing, we have two concepts. So one is the bucket address table, and then the other ones being the actual buckets, right? So in the bucket address table, we store the hash prefixes which are currently being seen. So by that I mean that is that you have the hash values coming from a hash function, and as I said before, we'll maintain a value I. This is called as the global depth of your hash file. And if I equal to 2, that means I'll have 4 buckets, so to say. Because when you're picking only the leftmost 2 bits in hash value, those 2 bits can be either 00 or 01 or 10 or 11. That is the only unique values which you can get when I equal to 2. When I equal to 1, you will get only two unique values, either 0 or 1, right? So that's how it goes. If I equal to 3, then you will get 8 unique values, right? So starting from 000 all the way up to 111, right? So depending on the value of I, which is the current value of I, this length will change, right? And this data structure, it is called as the bucket address table, right? So what this guy stores is, it stores pointers to the actual buckets where your records are contained, right? So when I draw a figure like this, what I mean is that if I get a record whose hash value uh, is starting with 1 1. No, it means the hash prefix is 1 1 when I equal to 2. Then I'll come here and I'll see that this entry is pointing to this particular bucket, and I'll go here and then fetch my record, right? So that is what it means. And similarly, if my hash prefix had a value of 1 0, I would come here and then follow this pointer to retrieve this bucket, right? So here something interesting is happening. So you can see that there are two entries which are pointing to bucket number 1, right? So what this means is that whether my hash prefix is 00 or if it is 01, right? In both these cases, I have to go and pick up this bucket. I have to pick the record from this bucket number 1 only. Right now, why this happens and all that, we'll get into that later. But for now, you take it that multiple entries from this bucket address table may point to the same bucket, right? And one more little small piece of assumption as we go forward. So in the slides which I'm showing here, I am sort of assuming that one bucket is one disk block, and in that disk block I can store two records. But, all the examples that you're going to see in the slides, they're sort of they're drawn with that assumption, right? If your one bucket spans across multiple disk blocks, you can easily change it. It's not a big deal, right? But for sake of easy understanding, I am assuming that one bucket is one disk block, and it is such that that disk block can store two records, right? Okay, one last thing before I go on. So here, I have two concepts which I am mentioning here. So one is called as the global depth, and the other one is called as the local depth, right? So what global depth defines is the maximum prefix length that you are going to see from your hash values in the current stage, right? So when I equal to 2, I'll see at most 2 bits from the left side. Okay, now local depth is slightly different. So local depth means that of all the records which are coming to this particular bucket, the leftmost I1 entries are going to be same, right? So over here I'll say that local depth is 1. Why is that? Because you see that in this bucket address table, both the entries of 00 and 01, they are the records, whichever come here or here, they are going to come to bucket number 1 only. Therefore, uh, if you see all the possible records that can come to bucket number 1, they will share a common leftmost 1 bit only, right? And that is the local depth of this bucket 1, right? So similarly over here, right? So here then the local depth of this bucket 2 is I2. It means that all the records that can possibly come to bucket 2 will have the leftmost 2 bits common, right? And here the local depth of I2 will be 2. And similarly over here, the local depth of I3 will be also 2, right? Two things to note here to make sure that you don't make a mistake. The local depth of every bucket in your hash data structure must be must be less than or equal to the global depth. In this particular snapshot, which I'm illustrating on the slide, the global depth is 2. And as I said before, the global depth defines the maximum number of bits that you are going to see from the left side to make a decision on the bucket, right? So in this particular snapshot, I equal to 2. That means the global depth is equal to 2. Now, local depth of every bucket must be less than or equal to 2, right? It can never be greater than 2. If in your example it is coming greater than 2 for this case, that means there is some error, right? Another thing to note is that it's sort of an you can say it as a thumb rule, that whenever entries in this address table, whenever multiple entries in this bucket address table are sharing a bucket for their record. So for example, in this case, entries 00 and 01, they both are sharing only one bucket for their records. Whenever something like this is happening, then you can pretty much rest assured that local depth will be less than the local depth, global depth. So here, local depth will be 1, because they both are sharing just only one bit, the leftmost bit, right? So that is why this is another way to see that if the entries are sharing a bucket, then local depth of that bucket is going to be less than the global depth. If the entries are not sharing the bucket, so for example this guy, the entry 10 has a bucket of its own, and similarly entry 11 also has a bucket of its own. So in both these cases, the local depth will be equal to the global depth, right? So in other words, all the entries which can potentially come to bucket 2, and theoretically they can come to bucket 2, will always share the left 2 bits, which, and in other words, the left 2 bits of all the records which are going to come to bucket 2 will be 10, and similarly the left 2 bits of all the records which can come to bucket 3 in this particular case will be 11, right? So this is the key concept of bucket address table, global depth and local depth. We'll have a lot of examples uh, as we go forward, but hopefully you got the concept. Okay, let's move forward. Okay, so this is just the definition of local depth, which I just covered. I'm writing it formally here. Okay, so now procedures to access an extendable hash file, right? So if you want to search for a key K, right? So there, let's say that your extendable hash file is hashed on department name, right? So what you do is that you compute the so for any given key. So for example, you want to get the records of computer science department, right? And your file is also hashed on computer science department. Sorry, your file is also hashed on the department name attribute, right? So for finding all the records of the computer science department, what will you do is that you're going to compute the hash value of the computer science department, right? Probably the name, and then you'll get your hash value, and then you are going to check what is the current value of I, right? Remember that the I was the global depth, right? So you'll check the current value of the I, and then you're going to take first I bits from the left side of this key, and then you look up the bucket address table to see which bucket the computer science records are contained, right? So once again, if your hash file is, let's say, hashed on the department name attribute, and you want to find all the records of the CS department, you'll first compute, if you'll first pass the CSC, that name, department name, through your hash function, and you'll get the hash value, and then you'll pick the leftmost I bits, and you go and look in this bucket address table to see which bucket contains the computer science records, and then you'll go to that bucket and retrieve them, right? So this is how you search for a key in the extendable hashing, right? Okay, insert operation. So insert operation is, again, it's similar to search, in the sense that first, whatever record that you want to insert, you're going to first compute the hash value. For example, if it's a new employee record, and you are storing according to the department name hashing, then for that particular record you will compute the hash value. You will take it his department name, and you pass it through your hash function, you will get a hash value, and then you will take the current value of I. You will see which bucket this record should go to, and then you go ahead and place it over there, right? So now if there is room in that bucket, yes, sure, no problem, the insert operation will be pretty straightforward. But if there is no space in that bucket, in the sense that the as I said, I'm assuming that one bucket is one disk block, right? So if that disk block is full, then you have to do some splitting, right? And when you do the splitting, you'll see that how this values of the global depth and local depth will change, right? Okay. So what I'm going to do is that in this video I'm going to give you a quick overview of the algorithm, and in the next video I'm going to cover the complete execution trace. Okay, so in case of overflow, there can be two kinds of overflow. One is when global depth is one is the overflow is happening in a bucket where global depth is greater than the local depth, right? So an example of that would be here. So as I said, this bucket can contain only two records. So let's say both the records have already come in. Now you want to insert another record whose hash prefix is also between either 00 or 01. So as per our algorithm, it should go here. But as I said, in the if you come across a case where this was already full and then you're trying to insert the third record into here, you cannot. So what will happen is that you have to split it. Now, how do you split it? Uh, so here the local depth is less than the global depth. So what you're going to do is that you're going to sort of create another bucket here, bucket 1 dash, make this 01 guy point over to the new bucket, and then you rehash, right? That's the procedure. You can just quickly go over it, right? So splitting when global depth is greater than the local depth, and bucket J is the bucket where the overflow has happened, and its local depth Ij is less than the global depth I. So as I said, what you do is that you create a new bucket, let's say Iz, and the local depth of Ij means jth bucket, and the zth newly created bucket, the local depths of both these buckets will be one more than the old value of the local depth, right? So J was your original bucket, Z is the newly created bucket, and local depth of Ij was local depth of bucket J was Ij, right? So now what happens is bucket J and bucket Z will have a new values of local depth, and that will be one more than the old local depth of bucket J, right? So you do that, and then what will you do is that you update the second half of the bucket address tables, which were originally pointing to Z, to point to J, right? And after you do that, you do the you basically rehash all the entries in the bucket J. Now when this is happening, what has essentially happened is that initially your bucket J contained two records and the third one came in, so now you have three records. And now in this process you created one extra bucket Z, right? So these three records will have to be rehashed across these two buckets, right? There's a good chance that they will settle down in one of the two buckets and the overflow will be resolved. If by absolute bad luck, if it happens that both the records over here had a hash prefix of 00, and the new record which is coming over here also has a hash prefix 00, then even after hashing even after doing this creation of new bucket and all that, all the three records will again go back here and cause an overflow. So in that case, it's more of an implementation detail, because you cannot keep splitting again and again. In that case, you just put an overflow bucket over here, right? So we'll cover more of this as we go into the example, but just thought you should know, right? Okay, so another thing in this case, which I wanted to know, which I wanted to tell you, is this statement. Update the second half of the bucket address entries, right? So this looks little strange, but there is a meaning to it, right? So when two entries are pointing here, right? So they were sharing the hash prefix of only 0, right? Because even though I wrote here 0 and 1, given that they are sharing, they're essentially having only 1 bit say, right? So now when you are increasing the local depth from I equal to 1 to I equal to 2, so what you can do is that you are basically taking one more bit from the left side over here to disambiguate your records, right? So when you take one more bit, what happens is that half the entries will point to the new one. So here you had only two entries, so therefore one entry stays here, one entry comes here. But if you had four entries pointing to the same bucket, then it will be slightly different. I think I have an example here. Just hold on. Yeah. Okay. So in this particular case, four entries are pointing to this particular bucket, which contains only one record, right? And the global depth is 3, and the local depth of this bucket is just 1. So that means, so basically all these four entries, they are just sharing 1 bit, which is the leftmost bit, right? So essentially here what is happening is that all the hash values which start with 0 are basically coming to this bucket only. Now if there is an overflow in this particular bucket, right? So let's say one record comes in, no problem, another record comes in, right? So that will be the case of an overflow in a bucket with local depth less than the global depth, right? So as per our algorithm, I'll create a new bucket over here, and I will point the last two pointers to the newly created one. That is what I was saying. So when I do this, what is happening is, see here we have 4, right? And so these 4 entries would be basically 000, 000, basically, and then 001, 010, and then 011, right? So basically the leftmost is common, whereas the other bits are different, right? So when I increase the local when I create another bucket and increase the local depth from 1 to 2, and I am pointing these two entries, the lower to 1, to the newly created, what is essentially happening is that for these two buckets I am taking now 2 bits to disambiguate the records. So the first two are still pointing here with local depth 2. So basically, hash prefixes 000 and 001. They both will be sharing a bucket, and then the hash prefixes the next two, right? So the next two would be 010 and 011. They will be pointing to the new bucket, right? So this is how this is how the splitting will happen when 4 are sharing to a bucket. Okay, so that was an overview of how overflow is handled in case of global depth being greater than the local depth. Now, if an overflow happens when global depth is equal to local depth, an example of that would be that, let's say take this bucket, right? Now, if overflow occurs in this particular bucket, okay, now if the overflow occurs in this particular bucket, you cannot increase the local depth anymore, right? You have already maxed out. The local depth over here is going to be equal to the global depth over here, right? So now if there is an overflow over here, now what you do is that you have to uh, increase the global depth itself, right? So basically each entry over here will spawn two children, right? One with suffix 0, the other one with suffix 1, right? And then both those children will be pointing to the same old bucket, and then again you reattempt insert, right? So I think it's best I cover examples on this, right? So hopefully you got a good idea on this.